Recall our illustration that shows how the operating system swaps between P1 and P2 for them to share the CPU. In this illustration, the process control blocks for P1 and P2 reside in memory, and the values of the CPU will change depending on which process is currently executing. Now we can more formally state that a context switch is the mechanism used by the operating system to switch the execution from the context of one process to the context of another process. In our diagram, this is happening both when the operating system switches from the execution of P1 to the execution of P2, and then again a second time when the OS switches from the execution of P2 back to the execution of P1. This operation can be expensive, and that's for two reasons. First, there are direct costs, and this is basically the number of cycles that have to be executed to simply load and store all the values of the process control blocks to and from memory. There are also indirect costs. When process 1 is running on the CPU, a lot of its data is going to be stored into the processor cache. As long as P1 is executing, a lot of its data is likely going to be present somewhere in the processor cache hierarchy. In the picture, we show a single processor cache, but in practice, modern CPUs have a hierarchy of caches from L1 to L2 down to the last level cache, and each one is larger but potentially slower than the previous one. More importantly, however, accessing this cache is much faster than accessing the memory. For instance, the accesses along the processor cache hierarchy will be on the order of cycles, whereas the accesses to memory will be on the order of hundreds of cycles, for instance. When the data we need is present in the cache, in this case that's P1's data, we call this that the cache is hot. But when we context switch to P2, some or even all of the data belonging to P1 in the cache will be replaced to make room for the data needed by P2. So the next time P1 is scheduled to execute, its data will not be in the cache. It will have to spend much more time to read data from memory, so it will incur cache misses. We call this the cold cache. Running with a cold cache is clearly bad because every single data access requires much longer latency to memory, and it slows down the execution of the process. As a result, we clearly want to limit the frequency with which context switching is done.